expecting me to understand physics in 7 minutes?
In 5 minutes, 4 minutes, 15 seconds,
This
40
sounds really hopeless.
Okay.
Down to the bottom.
Please remember your questions and then ask.
Bottom right, there's a little
dialogue around it.
there.
So I do research in nanotechnology and nanoscale materials at Cal State East Bay in Hayward. And so I want to talk with you a little bit about when you're playing Pokemon Go, you're thinking about what's really going on there, what allows me to actually play this game. So you might think about like history of computers for a second and like, you might be, wow, okay. And might be thinking about like, well, how did we get here, right? So the original computers were actually people who were doing computing. This became very famous as secret Rosies in the World War II era, which then leads to the mainframe computers, which took up the size of huge buildings. And then, does anybody know who that is? John Bakenbaker, the first PC. So like something you could actually hold in your hand. If we compare the specs of the Apollo mission computer, like the mainframe 360 from IBM, we see that we went from about 8 megabytes of RAM up to 8 gigabytes of RAM, and the price went down by a factor of about $1 million. One of the reasons for this has to do with the advent of solid-state technology, specifically semiconductors, which allowed us to have an exponential increase, doubling every 2 years the amount of transistors that you can put on a chip. You can think of a transistor as being like each decision is actually being made. And Intel actually makes these things very, very small and says kind of some not so nice messages about a certain Bill who owns a certain computer company. And so the way that this process actually works is something called photolithography, and silicon is actually a very great material for this kind of thing because you can actually put some kind of pattern on top of it, a mask, shine some light, and then dip the whole thing in a bath of acid, and it either eats away or doesn't eat away that part, and in that way you can etch circuits. Here's an interesting kind of circuit where it combines electrical and mechanical systems. So if there's a mechanical motion, you can actually, it changes the capacitance between these fingers of these teeth here, and you can actually know whether you're moving back and forth. This is an accelerometer. And so you actually have many different kinds of sensors on your phone that can measure anything from acceleration to the magnetic field around, so you can actually navigate. And you can actually also check your rotation. And each one of these kinds of things are sensors that are on board inside of the silicon chip that's inside of your smartphone. So displaying out to the world, you see all these little pixels here, actually. And so there's no white pixel, actually. If you notice, this is a zoom in. And after this talk, I'm going to give you a chance to actually see it yourself. It's tricking your eye because your eye only has cones that are sensitive to red, green, and blue. On the receiving side of things, we also mimic what's happening in the eye. And if the last pixels were 100 micrometers in diameter, which is the thickness of a human hair, these are 3 micrometers in diameter. So they're very, very small, right? We're approaching the nanometer scale, and we have millions of these pixels with these little filters on them that can mimic what our eye is doing. Now, when phones actually communicate to one another, they're using light waves. While I use that term very broadly, radio waves are a kind of electromagnetic wave. We also use fiber optics, but it's basically jiggling an electron on one side, and then it sends out a wave that causes electrons to jiggle on another side, and we call that as a signal. If you were to send light around the Earth, it would take 133 milliseconds to go around. So there are fundamental limitations to technology and how much we can advance with this, but we can also use the speed of light to our advantage. So if you're Squirtle and you want to talk to your friends, you can also use satellites to communicate to each other. And so satellite communication is we have about 28 or so public satellites that are actually pinging information, and if you pay a certain price, you can actually use them to also convey information. The way that triangulation works, and when you're driving in your GPS and you have the bubble getting smaller and smaller, basically, if you can see these circles around here, if you were in contact with one satellite, you could see how far away you were from that one, which means you're somewhere on this circle. And if you know a second one, you know you're somewhere on this circle. With the third one, you can pinpoint where you actually are. The touchscreen is also really cool technology. Basic idea is you send these little electrical pulses one way, another electrical pulse the other way, and when you touch down, you're changing the capacitance. You're actually interacting electrically with that circuit, and it makes like battleship coordinates and tells you where your finger is. Battery technology is another huge advancement that we don't often think about, but we went from having car phones. How many of you had a car phone or your parents had a car phone? Huge, big things, these things, and you pay $5 a minute to make a phone call. Now a little tiny battery, right, that runs for quite a long time. A speaker, also not a new kind of thing, but has been made miniaturized, the size of a thumbtack, in part a lot because of neodymium rare earth magnets and the developments that have gone on in that technology. If you apply a small electrical current across a little coil, it pushes a cone back and forth and it makes sound. Receiving sound, again, so the output and the input, we actually use micro electrical mechanical systems, the MEMS systems, and make a membrane on a silicon chip that's actually 1 by 1 millimeter, and small vibrations turn into electrical signals, and we're able to record that. So your microphone is also a very, very small device. Where are things going? Well, I mean, you can imagine chips in the brain, maybe projection being integrated, or being able to have all the information that you need as you look out into the world and augmenting your reality. Do cell phones cause cancer? I have to say probably not. And we can talk about that. But thank you for your attention. So.
I just want the chip that tells me who the person's name is. I want that chip. And it says, "You are now talking to Kathy. You met her 6 years ago. Thank you, Kathy. Good to see you."
There'd be a huge market for that.
But I want to access this.
I have heard that the accelerometers in phones are good enough now that you can use them as microphones.
Oh, okay.
The air vibrates the phone and the accelerometer picks it up and you can pick up sound that way.
Well, that sounds very interesting, right? So this idea that you have these little teeth here, and they're sensing these very small changes in motion. So one side of the teeth remains kind of basically fixed, and the other one's kind of able to bob around. So if you're speaking to something, you can cause that thing to bob around too. So somehow it's not surprising that maybe you could also detect sound by this kind of device. Another possible application, and I know that some people actually have watches that do something like this, but is to actually use the small motions, the very small motions that are happening. Maybe you have something in your pocket and it's moving around, or you have it on your wrist. Could you turn that motion into some chemical energy or electrical energy and be able to use that to maybe charge your phone? Maybe that would be like a possible application of that kind of thing. The other idea I wanted to just throw out there was just that an old Soviet spy trick is that when you're talking next to a window, you're actually causing the window to vibrate by several nanometers. And if you shine a laser onto the window and you bounce it off, it'll cause the laser to bounce, to fluctuate up and down a little bit. And if you record that with a photodetector, you can actually de-encode, or you can basically, eavesdrop. You can find out what their conversation is. So
Stay
cool.
away from windows.
I heard about that with like a potato chip bag as well.
Yeah, possible. So,
What?
Wow.
other questions? I know I flew by a lot of things really fast.
So about that cancer thing.
Cancer
can you
thing, yes.
expand on that?
Yes, please. So, I mentioned that radio waves are the way that we communicate. These are also kind of electromagnetic wave, and I think that a lot of people get concerned when they hear the word radiation. Electromagnetic radiation comes in a wide variety of colors, and a very, very small amount of that is stuff we can actually see. For those of you who are the long timers and you saw my talk about bees, you remember that bees see in the ultraviolet, right? So ultraviolet is actually like light that can be damaging to our skin. And if you go to shorter wavelength or higher energy, you can actually cause more damage to the cells. And so essentially what you're doing is you have a DNA, it's the double helix structure, and you're unbinding one of those, the G, C's, A's, T's, and so on. That's your genetic code. I think there's other people in the audience that are much more qualified to talk about that code, but the splitting apart your DNA is trying to repair this broken thing, and most of the time it does it correctly. Sometimes it doesn't do it correctly, and this is called a mutation. Most of the mutations don't actually matter, but sometimes the instructions keep repeating through this transcription process and don't stop, and that's called cancer. And that happens only when you have ionizing events, or in other words, short wavelength or high energy photons. But for low energy photons like infrared light and radio waves, which are the waves that cell phones are using to communicate, these don't have the possibility to damage DNA in that same sense, where they can actually rip apart electrons or damage the chemicals that make up their DNA. Yes.
Okay, so I'm just trying to figure this out. So let's say your very shortwave frequency radiation is the reason why it damages the DNA is because it's so small it can get in there and like wreak havoc. Like
can I use a assistant as an example here? No problem, right? It says low frequency. Don't worry, I know him well.
Can I try an example? So a very high frequency photon, being very small, has a lot of energy packed in. It's like a bullet. It's very destructive. But if I took the same amount of energy and used it to accelerate this sports ball at you, it would kind of bounce off.
Yeah.
So low energy photons are, and the size scale, am I right, is kind of comparable between a bullet and a...
Yeah, I think I get it.
Yeah.
Yeah.
So we need to make photons more lethargic in order to keep us safe. The high energy ones are dangerous.
Well, unfortunately, they all travel at the same speed, but the wavelength is different.
How do you control the wavelength?
Maybe that's more genetic.
It's how much energy you put into it and how it's produced. The really fast. I should let the physicists talk, shouldn't I?
If you jiggle an electron, then you create electromagnetic radiation. And the faster that you jiggle up and down, which I symbolize by shaking just an up and down, you produce the high frequency waves. In other words, the spacing between each wave is becoming shorter, basically. So we call this a shorter wavelength. But essentially, since all the waves do travel at the same speed, that means that when that wave gets to you, it's going to cause an oscillation that's much faster compared with something with a longer wavelength.
So when you jiggle an electron, you're creating like an E field, and that also makes a B field, and it also makes light.
Yes, that's right.
Does this light interfere with B fields like magnetism?
Well, so actually, one of the kickers of the late 19th century was that waves of electric fields cannot exist without waves of magnetic fields, and so the two actually co-create each other through free space, and they don't need any matter to go through. So at the time of Maxwell, then it was basically thought that if you wanted to have a magnetic field, you should have a current. But in space, there's no matter, so there can't be any current. So they thought, well, something's really strange then with our equations, because there doesn't seem to be any way that, so if you have a wave of an electric field, which was well known, then they said, well, then if there's a changing electric field, according to those equations, there should also be a changing magnetic field. And if there is then any magnetic field, there should be matter. And there's not matter. So it actually is that the electric field and the magnetic field are actually moving together in lockstep. So like, I guess one's going like this, the other one going, going up, down, and the other one's going left, right, as they're moving through space together. They're co-creating each other. They cannot exist without one another, which is a very bizarre and profound consequence of physics. So.
And then how does light play into that at all?
So light is that wave.
That is light?
The wave of the electric field, or I could also say the wave of the electric field and the magnetic field
together
is light. That's what electromagnetic radiation is, and that originates from an oscillating charge or any charge that's accelerating.
Can you bend light?
Light can bend by gravity, and so you might think of that the gravitational field itself is not really like a field in the sense that maybe you've tried a Van de Graaff before and you've kind of felt this sort of staticky electricity kind of stuff. The gravitational field could actually be rethought of as a warping of space itself. So you could actually, if you think you're traveling in a straight line, somebody else might look like you're traveling on a curvy line. Yes?
So we've talked about slower frequencies and higher oscillation. What's the difference in function when it comes to phones?
What's the difference between what?
In function between the sort of slower oscillation light waves and the faster oscillation.
And the faster oscillation waves? I guess my main takeaway point is that the frequency that phones use is around 1 to 2 gigahertz, okay? So that might sound like a lot. You're like, whoa, that's a billion times a second that this thing's oscillating, right? But if you compare that to visible light is a million times faster, a million times more oscillations. For every one oscillation of an electron for gigahertz radiation, there's a million times more oscillations for the light that we're seeing from this lamp here. So if the cell phone's causing me some trouble, wow, well, this thing's really going to be causing me some trouble, right? So that's the kind of the logic that I want to use. And then also if you relate that to the scanners at the airport, the scanners are also using millimeter wave technology, which actually turns out to be about tens of gigahertz, right? And so that also is non-ionizing radiation. So you can do like this kind of thing, and you can be illuminated with this light that you can't see, but it's not actually able to damage in that sense of ripping apart DNA, such as X-rays can.
So there's also backscatter X-ray scanners at the airport, right? Or have they given up on that?
As far as I know, most of it is the millimeter wave technology. The one where you go like this and you do the thing, and they have the like that. That's one side is an emitter of millimeter waves, and that is only just working by having a bunch of antennas that jiggle electrons. And on the other side is essentially a camera or a detector. But you could think of it as just a line detector. But by revolving around, they can reconstruct a three-dimensional image of you. So.
Yeah, at least in the U.S., the TSA retired the backscatter ionizing radiation a couple of years ago.
But it's a more expensive technology, so yeah, that's the only downside. So I mean, in a lot of developing countries, this is not something that's realistic. Yeah.
They just take you into
Well,
Well,
at the,
so okay.
at the 1 to 2 gigahertz range, like, is it possible to be resonating, let's say, molecules in your brain that could be fried?
I guess like I don't want to say that it's impossible, but so far no one has found such resonance, and I'm open to the possibility that maybe there is some kind of health problem that could arise from this kind of thing. And you know, it's like smoking, right? So when smoking was kind of all these campaigns against smoking happened, and people actually stopped smoking, then the peak of lung cancer, it also correlates, but it shifted out 20 years, right? And so if you look at that in public health records, it's a very interesting graph, because could there be something that we just don't even know that's harming us, and it's dormant inside, right? It's totally possible, but I would wonder what would that mechanism be, one, and the other one is, is that a risk, or are you more at risk from walking out into the street, right? right? Or trying to do this while you're like driving and brushing your teeth, right? You know, like, I mean, like those things are like, I think, far more risky, like billions of times more risky, I think, than any kind of exposure to the radiation that you're getting. Plus, this is only like 2 watts of radiation, right? So when you think about something like this, it's like 20 watts, right? So like, it kind of gives you like a sense for like, it's not that much electromagnetic waves, but still, I don't want to say it's not possible. Like, I mean, I'm open to that possibility.
I just wanted to say you forgot death by selfie.
Say again? About making selfies?
Death by selfie is
Death by
a
selfie.
huge risk.
Death by selfie is definitely a huge risk. Another thing that I wanted to invite you all to try out is, you saw that little section that I talked about, the LCD, the liquid crystal display that's on the front of your smartphone, right? And so I brought something that I 3D printed, and I invite all of you to try taking a look at it. If you really like these things, you can take one home with you. But basically, the way that you would use something like this here is you take off the case of your camera, and it works with any Android or iPhone or whatever. And there's a little glass bead on here, which is actually one of the original ways that people did microscopy. So it acts as kind of a lens and focuses down. So you can put this over your camera like that, and then you go into the camera mode of this thing like this, and then you can actually hold it up to like a screen, like this one, for example. And let's see if I can try a demonstration. I don't know if this will work out well, but you can give it a shot and try looking at a few different things. So you see how there's like kind of an open spot there, and then when I hold it up to here, perfect. Yeah, so you can see, you can literally see that this thing has no white pixels. It's actually reds, greens, and blues. So I invite you to come up and.
One?
Oh yeah, absolutely, yeah, sure. So I'll just I don't know, I'll leave these up here. You can come and pass them around or something like that. But yeah, try it out. It's kind of a fun thing. Kind of helps you to see the world that you can't really quite see with your eyes. And so this is not necessarily the nano world, but these pixels are 100 microns, which is starting to approach nano scale. So it kind of gives you an idea that like all this engineering that went into these phones. This has been really heavy duty in the last 20 years or so. We were getting to these very, very small features. So.
Cool. Where do you see cell phones going, like improving at this point?
Well, so I kind of had that like slide that I ended up having to kind of rush through it. I mean, like, I don't know, and I guess when I think about this futurist kind of stuff, I always stop to think about functionality and like whether it's really useful to us, and I feel kind of duped sometimes about how. I start to feel like my phone runs out of batteries and I get all anxious and I feel like, well, then how am I ever gonna find my way? Really, is it really that hard? And I just, we were lost for decades. I know. All those old geezers out there that just didn't know, right? So yeah, so I don't know. I mean,
have you ever tried to go to a gas station and buy a map?
Buy a map, exactly.
It can be done.
Yeah.
You can't. They don't. It doesn't exist.
Sure. So I mean,
they don't remember when gas stations sold maps.
We live in Silicon Valley, right? It's really easy to get caught up in the hype of like the next big thing, and to say, oh wow, we're gonna have microchips in the brain. We're gonna have projectors that's like that are like integrated with your phone, or you're gonna have it on your watch, and it's gonna like tell you everything, and like. But I mean, like on some level, we're getting in lots of information, but is it quality information? And so I guess. Maybe what I would challenge all of us here, and also kind of the greater community of Silicon Valley, is to question value, not just functionality, and how how we're making decisions based on values, not based on kind of what seems cool or what seems like it might sell to people.
I think a map is a good example, because what we do now with a Google map or whatever map you're using, Waze or whatever, everything you see is based on information based on where you are. It's all based on you, as opposed to an old-fashioned map, which none of us use anymore, including me. Let you see, but you also saw what was there. It wasn't based on you. It was based on, here's the world, and you had to find yourself on it. Now we find ourselves, and the world is related to us.
That's right. So I don't know if this is true or not, but I do get the sense sometimes that our younger generation tends to be a bit more narcissistic and thinking in a sort of. But hold on, before you agree too strongly with me, I bet your parents thought the same thing about you too, right? So
they were also right.
And also, like, to be fair, 500 years ago we used to think that the Earth was at the center of the universe, right? So I mean, so there's it's a bit more complex of a story, I suppose. But I wonder if this kind of level of the way that we relate in terms of how it relates just to me, if that's subconsciously influencing our relationship and our way that our communities are forming. So. Yeah.
That's the fascinating thing. That's where I want my PhD. Is what's this doing to us socially? I think it's fascinating.
Last question. Somebody?
I just wanted to intersect something regarding the comment about younger generations. I'm quoting: "The children now love luxury. They have bad manners, contempt for authority. They show disrespect for elders, and love chatter in place of exercise." Socrates.
Yeah. Where are you?
Good. Thank you.